So, thank you very much for the invitation to speak here. So the title, essentially the content is described here. How is it? Ah, no, it's here. Yes. So we start with xn. So this will be an n-dimensional complex projective manifold, and for arithmetic considerations, it will be defined over a number field. And K prime will always describe a finite extension of the initial base field. So again, number field. And usually we will have to consider a sufficiently large extension, so in order that the geometry implies the arithmetics. And so the aim essentially so the aim here, and probably for in arithmetic geometry, this is the general aim. This is to describe in geometric terms, and so I will make this more precise after. What is meant by this? X of k prime, for k prime sufficiently large, when x is defined over a number field, and C of x, this is the set of entire curves. So what are these entire curves? An entire curve is just a non-constant holomorphic map from C to X, the complex line to X. A priori, this is, the interest here will be mainly in transcendental maps, not algebraic maps. The algebraic version, if you want, is precisely a rational curve, so holomorphic maps from P1, the projective line. So these are the ones which can be compactified to at infinity. And so why do we consider these two things? Essentially because if there are conjectures originating from long and then extended and precised by Voita, maybe later, saying that essentially there should be a correspondence between geometry on the one side, arithmetics on the other side, and on the third side, really, this set of entire curves. Voita, for example, he described an analogy and even a dictionary between given holomorphic entire curves and infinite sequences of rational points. And actually, with the conjecture which we'll state, it's possible to prove, assuming these conjectures, of course, that having an entire curve implies the existence of an infinite set of rational points, maybe after a finite extension and conversely. So this is essentially the reason why we'll consider entire curves, and also there are in many situations, and we shall describe one, in which the arithmetic side is actually not accessible by the means existing today, while the holomorphic side can be proved. So this is essentially what will happen here. So first, in the case of curves, so n is 1. So n is reserved always here for the dimension, complex dimension of xn. So x is always of dimension n. So this is the case of curves, and so the geometry, this is given by the genus, and so this is a famous theorem of curves. Everybody knows this here, that we have equivalence between this geometry and also the non-existence of entire curves. And the non-existence of entire curves in this situation, this follows fairly easily from the uniformization for curves of genus 2, because they are uniformized. Their universal cover is the unit disk, and then Liouville theorem says that bounded holomorphic functions from C to X to the unit disk, so they are constant, and these maps can be lifted to the universal cover. So now on the other side, of course, then we have, when G is less than or equal to 1, then we have this property. So this is for obvious reasons, essentially. So you have only rational or elliptic curves. And there is a difference, actually, between G is 0 and G is 1. In the first case, you have actually algebraic maps from C to X, which are non-constant. So you have algebraic entire curves, while in the second case, all of them are transcendental. So this is a difference. And now the generalization, which is, we shall see this later. So now, actually, the genus, this is very hard to, there is no suitable generalization in higher dimensions, but we have to consider instead the canonical bundle. And so what is the being of general type? Kappa of X, let me tell that kappa of X is n. I will not give in general the definition of this. There is not enough time. This is kappa of X, and here, this is the canonical bundle of X, is n. So this means that there exists a positive constant, C, which depends on X, such that we have H0 of X and then Kx tensorized n times. Then this is maybe, no, okay, this is sometimes m power n. So this means that we have, when we take powers of a canonical bundle, positive powers, then we have more and more sections, and actually we have a maximal possible growth of this number of sections. And so this is the general principle in birational geometry, that actually the positivity of a canonical bundle permits essentially to give, to a certain extent, a qualitative description of the geometry of X. So this is the general principle. So we don't know what is the geometry, but if we have information on the positivity or negativity properties of a canonical bundle, then we can, in general, say something. So this is the generalization of hyperbolic curves. If you want, well, okay, I will not say more. And so now we have G is less than or equal to 1, and so this is, in some sense, a kind of a new definition. This generalizes to X is special. So special, this has a precise technical meaning, and so this means essentially that the cotangent bundle has not maximal positivity in the following sense. So I will maybe describe this. X is special. This is the definition here. If and only if we have the following. So we have kappa of X, L. This is less than P. For any P positive, and here, and we have L instead side of omega P, and so this is always the same P which appears here. This is rank 1. Rank 1 is say a line bundle. So if we take all possible line bundles inside of omega P, of all omega P's, we should never get the equality P. And so what is the meaning of this? The meaning of this is in some sense the opposite of what is appearing here. And so kappa of X, L is strictly less than P. This means that, again, that there is a positive constant, another one, such that we have H0 of X, and here we take the positive powers of L, which is less than or equal to C times, and here we have M, and this is the exponent P minus 1 here, which appears. And this should be for all positive. And here, in general, there is a theorem of Bogomolov. I mentioned this briefly. A theorem of Bogomolov, which says for every X, for every L inside of omega P here, so this is universally true, we have this kind of information, but here with P, P minus 1 replaced by P. So we have P. So this means, this is in a certain sense, you see, here we have this N. So the exponent here, when you are in omega p, is not controlled by n, but it is controlled by p, which is the p in yes, which is this p here. So in some sense, you have no maximally positive line bundles inside of omega p for any p positive. So this is the meaning of special. So let me explain a little bit why this generalized G less than or equal to 1. So assume that we are in dimension where we have n is equal to 1. So we have a curve, for example, and in this case we have only one possibility for p, and this is p is equal to 1. But in this case, omega 1 will be kx. So we have only this possibility. So this means that for curves being this means that x is not of a general type. And so, as you know by classification, so this means that we have either elliptic or so. So this is the reason, but in higher dimensions, the situation is a little bit more complicated. Maybe I should, I don't know. I wanted to put this later, but maybe I will give the explanation right now. Let's see a remark, which is the following. If x is special, then this implies that for any f for x, which is to some zp, I take a dominant here, rational map, to manifold here, which is p dimensional with p positive. And so what I claim is that if x is special, then z is not of a general type. Is not of general type. So I will give the explanation, which is very simple, in fact. And so this means that essentially, if something is special, it doesn't map onto something which is of a general type. This is actually specialness is much stronger than this, but one has to give many more explanations to see this. And why is it this? But because assume that we have this, then we can lift here kz. Kz can be lifted in this situation because everything is birational and so on. Kz, this will take L is f star of kz, and this is inside now of omega p of x, and this is the same p as the p which appears here. So you have the same p, and so assume that that z were of a general type, then we would have that kz of kz. This will be equal to p, and actually this is a general fact. Then this is exactly the same thing as kx and f star of kz. And so we would get a contradiction to this property. We would obtain a line subbundle which is of top dimension. And actually the analysis of this situation leads to this, and this is but the specialness property is not described only by this. This is a strong one. And now the conjecture L, as L is for long, of course, is that x is of general type, is equivalent to x being generically Mordellic. And so generically Mordellic, this just means the following. In the arithmetic side, that there exists some omega w, which is inside of, this is for x here, for x, and this is Zariski closed. So this is an algebraic subvariety, such that maybe I will first state this for entire curves. For any h c to x, which belongs to the set of entire curves of x, we have h of c is contained in x minus w, which is u here. Thank you. Yeah, of course. Thank you. Sorry. Because is inside of W. And a priori, this W is expected to be exactly the union of all special subvarieties of X. If you want an example in which this situation has been studied and even proved, this is the case of subvarieties in abelian varieties, where you, for example, the ones which are of a general type and so on. So you have, this is this kind of situation. And on the arithmetic side, this is then that x of k prime here, that x of k prime intersected with u, which is this time x minus w is finite. For any k prime. Yes, I'm sorry, because here I didn't have room enough in order to put the quantifiers. But for g is equal, larger than or equal to 2, x of k prime finite, this means for any k prime, k prime, while in the next line, this is, where is it? Ah, yes. So this is for some x of k prime dense for some k prime. There exists. I have forgotten to say this now. And now, once you have answered the next one, because you have these two opposite worlds, so you have the general type on the one hand and special ones on the second hand. They are completely opposite in some sense. And so the conjecture also is that they should also this should be reflected in the arithmetic and analytic situation. So mean x potentially dense. So x potentially dense, this means when now on the arithmetic side, after a finite extension of the base field, then you get a Zariski dense or even a dense set of k prime rational points on x. And for the on the analytic side, the expectation is that there should be entire curves which are, you can choose, Zariski dense or even metrically dense inside of X. So this is the conjecture S. And once you have these two conjectures, there is a structure theorem which tells you that you can then expect to describe EC of X essentially and X of K prime for any X. Because you have a splitting theorem, which is the following one. So this is the core map. So it says that for any x, you have a certain fibration in the sense of connected fibers from x to c. I'm a little bit simplifying this. C is in general only, this is slightly meromorphic, but not very much, and so that its general fibers are special, and so the orbifold base is of general type. Let us forget for the orbifold world, we can forget this for the time being, and so assume that we have no orbifold world, so this means that C now, this is of general type. Assume that we are in this situation, so this corresponds to the fact that delta C is 0, and if you prefer that you don't have multiple fibers in a certain sense in codimension 1. So, because this delta C, this is a Q effective divisor which encodes the multiple fibers in codimension 1. I don't want, will not have time to speak of this. So assume that now that C is of general type, so we are in the following situation. We have our X, and we have here this C, and we have this map, small c, this core map here. And so we have the fibers here. The fibers are special fibers. And so what is the description, for example, for the entire curves? So because C is of general type, if we apply long conjecture, what happens is that we have a certain W here, such that all entire curves here, from the complex line to C, they have to be contained in this. So now assume that we have a map here from C to H, maybe, to X, which goes this, and then we compose, we consider C composed with H. And so this composed map here, this will be either it's constant or it's an entire curve on C. And so if it is not constant, then it has to be contained in W, and so you are here. And so this means that the only entire curves are in the fibers, except maybe over this subset here. So this is the description, and I will not give the description, but you have something similar on the arithmetic side, and you can imagine what it is. Okay, so you have something similar. But so I save some time in order to a little bit further. Yes?
Conjecture L, how does it work when X is a product of P1 and a genus 2 curve?
That's exactly the situation I didn't want to describe because I wanted to save time. But this is very easy. So you have, for example, if you have F, and here F, a surface S, which is something F cross B, and B, this is the base here, and here we have F. And assume that this is a curve, G is less than or equal to 1, and here this is G greater than or equal to 2, and so you can prove what you want in this situation, in the arithmetic side or in the...
Not of general type?
This is of general type. The base is of general type. No, certainly this is one of these situations. In this, if you are in this situation, so then the core map, this is just the fibration over B in this situation.
But this space, you call it generically Mordellic, the total space?
Yes. No. What is called generically Mordellic is only when you are in the general type case.
So the two, I'm confused because it looks like the two sides.
Did I write something? Yes.
From the right to the left.
Yes. If this is generically Mordellic, then this has to be also of a general type. But this is not maybe, yes, you are right. Maybe the statement is not quite correct, said like this. Okay, I should think in order to put this. You are right. Sorry, yes. Okay, so not anything is either special or generically or Mordellic or potentially dense. Sorry, yes, you are right. I should have a statement.
No, because over an extension you could have other points, and then the fibers would be filled with these points, and this means that the complement will be not finite.
Generically Mordellic, I think, nevertheless, this should be true.
Outside of the...
Are you saying that this is?
Yes. So, sorry, no, I think this is correct. Nevertheless, okay, this is correct. Nevertheless, because in general, if you make a further extension, then you will have infinitely many points here in the finitely many fibers.
It's the same for the genus 2 curve by itself.
No.
In the genus 2 curves, then outside the set is finite in any case.
Yes.
Yes.
Yes, I didn't write what was the arithmetic side, but the arithmetic side forbids to have, for example, in one of these fibers, infinitely many points. Generically Mordellic, this means essentially I wanted to save some time, but I can't. So generically Mordellic means the following. I thought I had written this. Yes. That there exists some W such that x of k prime intersected with x minus W. Of course, this is inside of x and different, not equal. That this here is finite for any k prime of k. Huh? Okay. So this should be finite. And so here, in this situation, in the product case, you would have, after a sufficiently large extension, you would have infinitely many points outside of this W. Ah. Yes. Okay. Now, let me. We are turning to X rationally connected manifolds. So RC means rationally connected here, and so manifold, for example, this is over C. Now this is rationally connected if and only through two generic points. Say, then you have a rational curve going through these 2 points. So you have X. You take two generic points, X and Y here, and so there will be a rational curve. There should be a rational curve. Over this, of course, the immediate example is Pn now, and if you have Pn because you have lines, and Pn, this implies now that this is rational. So rational meaning birational to Pn, and so this implies now that you have unirational. This means that this is that there is a map from Pn, rational dominant map from Pn onto X. X equals Pn, X equals X is unirational. And so if you have a dominant map, not necessarily rational, this means that this dominant map is of degree 1, and here the degree can be larger than 1 or anything. And this implies, obviously, then that X is rationally connected. So you have this sequence of implications. And another implication that we have is when X is Fano. Fano means that minus Kx is ample. And so here you have just an information on the canonical bundle. And so here we have extreme negativity of a canonical bundle instead of, this is really the completely opposite to general type. So the minus Kx now is ample. X, and you have this implies when X is rationally connected. And so the proof here uses the characteristic P methods which have been developed by Mori. And so we have this. Now we have the implication, about the reverse implication. This is completely open question when we are in dimension n or equal to 3, and this is expected to be in general completely false, that you have many more manifolds which are rationally connected than those which are unirational. This is important for the sequence, for the sequel, and here, but on the other hand, when n is in smaller dimension, n is equal to 1 or 2, then you have the implication even to rational. So, as you certainly know. So, but a priori, there should be a very big difference between these two classes. Now, a small remark is that this is the easiest class of special manifolds, that X is rationally connected. This implies now that X is special, and there is a very simple reason for this. This is a very strong form of this, because you have H0 of X, this implies then the H0 of X, and if you take the positive tensor of omega 1 of X, then the set of sections is always 0, because you have lots of rational curves and they will impose the vanishing of all these sections, and so this implies this is a very strong form of specialness. So you have this, and now so this means that we expect in this situation, according to the conjectures S which was made before, and so this means then this should be means that this is potentially dense. that X should be potentially dense if it is rationally connected. And so potentially dense either in the arithmetic meaning or in the analytic meaning. And so in the arithmetic meaning, the situation is completely open, if you want, except maybe for, in dimension 3, many cases are known, but in general, yes, I should notice that when X is unirational, everything, this implication is okay because you have already a dominant map from Pn to X. So everything is completely easy. So the non-obvious point is precisely the difference between unirational and rationally connected. So what should, and now we have the following result. Yes, on the arithmetic side, this is completely open, this implication. Rationally connected implies potentially dense. But on the analytic side, we can prove this. So now this is a joint work with Jörg Winkelmann of Bochum. Bochum University. And so the next results also are common work. And so we have the following. If we have a rationally connected manifold, and if we are given inside of X any countable subset, so a sequence x1, x2, xn, and so xm, and so on, then we can find an entire curve which goes through all of these points. And in particular, if the sequence, if n is dense inside of X, then you have also a dense entire curve of curves inside of X. And so I don't give a stronger statement, but also you can make this a little bit more precise. If you have a subset, an algebraic subset inside of X, which is of codimension 2 or more, then you can also avoid it. If n avoids this subset, then H will avoid also this subset. It's possible to do this. And now, a consequence of this is a kind of analytic version of a weak approximation property.
This is on published archive?
This is on the archive, for example. Yes. This is the same, but except the following. You can so the statement is this: if you have a sequence of points, so then you can construct also an entire curve going through all these points, but you can do slightly better if at each point, for example, you are given the derivatives up till say that this is the point xm here, and so if you are given the derivatives up to a finite order km, then you can also impose these conditions. And the idea is fairly simple, is that if you blow up at points, for example, successively rationally connected manifolds, then they remain rationally connected. This is not completely obvious, it depends on the definitions you have taken. No, not, yes, infinitesimally near points. You can make successive blow-ups into into a point. So you take a point, you can blow it up once, and then a second time, and so on.
But you have infinite many of them.
Huh?
But how do you make it agree with the jets at infinitely many?
At infinitely. So you have to look again into the proof and to make induction. You don't blow it at once, you blow it successively. Yes, not directly. Yes. This is adaptation of a proof, but I have not explained the proof.
Who is AWH?
Analytic weak approximation property. So you have, and another thing that we can make Yes, is now also analytic version of Hilbert property, which is the same. Maybe this is a little bit long to explain, but essentially this property, this analytic Hilbert property, has been formulated by Corvaja-Zannier, and Corvaja-Zannier conjectured actually that this would be true for the rationally connected manifolds in particular, and so we can prove this. In fact, essentially with this. So the idea. So what is happening is this. So you start with X, for example, which is a rationally connected manifold, and so you have a certain cover, I don't know how to Y here, and you have a finite map here to Y, but you insist on the fact that this is actually ramified somewhere. So you need really to have a ramification somewhere, and so what you, in order to produce this kind of holomorphic map or dense entire curve, which doesn't lift to X, so you want to impose that you have no lift of this map to Y. So it's not a composed map, so you can send your X, so you have this H, and you don't want to have an H prime here, which goes to this. And so the reason is just that you take your dense entire curve, and so what you insist is that at some intersection point, and you can easily do this, now that the intersection is transversal. And this prevents from having this, at least when the ramified cover is Galois. If it is not Galois, this is more complicated. One has to make further arguments in the case, non-Galois case. But in the Galois case, this is a fairly direct consequence. Now, a kind of small application which I would like to make is this. Excuse me? Yes. This is a finite ramified cover. Yes. Thank you. No. Yes. And now the next example of application is the following: this. Assume that we are now we are in P3. This is P3, and here we have a smooth sextic surface here inside of P3. And so the claim is that there exists lots, actually, of dense entire curves inside of P3, which are everywhere when each time they meet S6, they are tangent, maybe not to order 2, but possibly to order 4, 6, and so on, an order divisible by 2 at each of these intersection points. So you can do this. Why is it so? The reason is that is very simple, is that there exists now a ramified cover pi from some x here. We take the double cover of P3, which is ramified along S6. Here, and so this exists because the degree is even, and so we have this cyclic cover, and this cyclic cover now, this is Fano. This is Fano, and this implies when this is in particular, this is rationally connected, and we have this property. Why is it this? Because if you can compute, because kx, this is pi star of kp. 3 plus 1 minus 1/2, which is 1/2 actually, or let's be 3 of S6. And so if you compute, here you have -4, and here you have +3, and so this is -1. So this is the inverse image of O of -1, and so this means that this is Fano. And so because this is Fano, and now, so we take any dense entire curve inside of X, this Fano threefold here, and we project it down, and it has immediately this property because of this ramification property. And so, although we are not, although we have a proof here, and assume, I would like to say that this is one of the examples where it is not known where this is unirational. There is no example which is known to be unirational. This is maybe expected not to be unirational, but okay, so this is an open question. So we can apply the result here, but we are completely unable to prove the result directly on P3 and with S6 without going to this cover. And so this means that I will describe a little bit the proof. This means this is just because we are not able, at least there is presently no theory of deformations of rational curves which are tangent with tangency conditions. This is what is missing to prove this kind of result. And so, did I want, how much time do I? Okay, let's, now I will maybe give an idea of the proof of the theorem. Actually, the proof is surprisingly simple once one has the available techniques, which are already at least 20 years old. And so the result is this. Okay. Maybe.
The statement that you just said, can you repeat the statement that you said you didn't know how to
prove? Yeah. Yes, how to prove the existence, for example, of a dense entire curve, which is everywhere tangent to S6 directly, without going to this. To proving, so you are given just P3 and S6, and you know that this is Fano. This is Fano because the degree here is strictly negative. And so you would like to have first many rational curves which are tangent to this, but this is okay. But now you would like also to have this property. And so what is missing is some theory of deformation of rational curves with tangency conditions.
Deformation is okay, maybe the generation is the... Deformation is okay, but maybe the generation is the...
Yes, the limits, limiting properties, yes. Yes, this is open problem. Yes. And so you have this statement. I will make a drawing just to explain what is the meaning, because you have lots of things. I think actually the situation is very simple. So we have here a certain map. Excuse me. This is Fm of P1 here. So we have a certain map here. I have forgotten here, I didn't forget, but I didn't write some normal bundle conditions. We need some positivity properties of normal bundles here for the rational curves, which are considered. I didn't write it to simplify. But so we have a certain number of points. So we have x1, x2, and so we have a certain xm here, and so we have already constructed a rational curve here. So we have certain points, a1, a2, and so this is am. They all belong to C, and so this is maybe, this is infinity, which goes to a certain point. I write this point here. So we have a certain rational curve going through these are the m first point of our sequence n. N was written as a sequence x1, x2, xm, and so on. And so we have first points. And we want to add one further point, which is xm plus 1 here. So we have already this now, and so we want to make it. So we draw now, this always exists, another rational curve here. This is a g of P1, and so the point here, this is 0 going to this, and this is maybe the point 1 going to this xm, and here we have infinity which goes to here. So we have now two rational curves. So once this is given, because by rational connectedness, we have also a further curve. And now, what is the main point here is the so-called gluing technique of Kolar-Miyaoka-Mori. I think this is something like 92. Something like this. The gluing technique tells you then if you have sufficiently positivity here, and this is the simplest case of there, then that you can find now another rational curve which goes arbitrarily closely to the union of these two curves here now, and in such a way that here this will be close here, for example, to a certain. So this is a large disk D of 0 Rm here, which contains all these points, for example. And so you can do this, and actually, which is epsilon close to this one on this part of a curve, and it will be also epsilon close here, for example, and even everywhere, actually. And here what you have to check is that here this xm plus 1 now, this will be given by a point. This is the map fm plus 1 of p1 here by something which is sufficiently away from this Rm. So at least Rm plus 1 will be the parameter of this point. And here, now you have to change this slightly, the A1 to a certain B1, A2 to B2, and so AM to a certain BM with a very small change. Here you have this, and here also you will have something some parameter space. So this is the idea. So the important point is that if you have two positive rational curves, then you can approximate them by a single curve, and you have to control the parameterization. So this is essentially the point. And once you have done this, you just have to make induction on M. So you start with a single point, then with a second point, and with M points. And because here you have this epsilon closedness, you will take epsilon M, which will be a certain epsilon. You can fix it arbitrarily, and divided by 2 power m plus 1. So this will imply that on this disk Rm, which will be at least, Rm will be greater than or equal to m, actually, then you will have actually uniform convergence of your maps, and so you get at the limit a point. So if you want 99% is completely algebraic geometry, and you have just a simple argument for the convergence. There is almost no analysis.
So when you move from m points to m plus 1 points, now the neighborhood will go all the way through
yes.
m plus 1?
Yes, yes, you have this approximation, but yes, absolutely, yes, you can put this epsilon here. Okay, yes. So you have this, and so now this is maybe okay. So you have this. Now I have maybe a little bit time to speak a little bit of special manifolds. What I wanted to say, yes, it is also possible, but only in the case of surfaces. Using results of LMMP, it is also possible if you have X is S. This is a rational surface, but now with some singularities and quotient singularities. And now it is also possible under some conditions, because this is not true in general, to have also dense entire curves into such rational surfaces, but which avoid the singularities. It's possible also to do this. But one has some conditions to impose, because this is completely wrong in general. I don't have time to give an example. Now I will come again about these special manifolds. So recall the definition which was given. So I already mentioned that there is a result of Bogomolov which says in general that the Kodaira dimension of these line bundles is always bounded by P. X special, yes. So I mentioned already this. So the next thing in particular, so we have in particular, if X is special, then it is certainly not of general type. You just have to take the identity map. And now we have already seen this. And now an important class of examples is when kappa of X is 0. Kappa of X is 0, then this X is special. And so this is a very important class. And in particular, this special case of this is when C1 of X is 0, so the first Chern class of X is 0. So if you prefer, in more algebraic terms, this means that the canonical bundle has degree 0 or on any curve, or equivalently that it is torsion. Distortion. And so this is a second class, and so you have lots of examples, of course, for the abelian manifolds. Abelian varieties are, of course, special. Then you have the Khafre surfaces, the hyperkähler manifolds, and then Calabi-Yau. And if you take the hypersurfaces of degree n+2 inside of P n+1, then you have these are also special because you have this kind of property. So there is a big difference actually between this condition and this condition. Here we can show that X is special, but here if we are in this situation, then we have a much stronger conclusion. But so now the only point is that in general, X is special. This is not, in contrast to what happens for curves, special manifolds are not either, say, something like rationally connected or with kappa is 0. So they may have, I will state this after, they may have essentially arbitrary Kodaira dimension, but nevertheless, they are built from orbifold pairs. Now, this is important to have this, which are even rationally connected in some sense, or with kappa is 0. And so this means that we have to consider more general case, not only X's, but also some type of divisors, which looks as ramification divisors here. So essentially, this means that when we want to solve, for example, this conjecture S for special manifolds, we have to go to the larger category of orbifold pairs. But it will be sufficient to solve it in the rationally connected case or in the kappa is 0 case, but for this larger category. Now, but essentially, yet, this is what I said before. Actually, if you take any possible Kodaira dimension, which is like this, I'm sorry, I don't define it for people who know, that's good, but otherwise, they may have arbitrary Kodaira dimension, except, of course, the top one. On the other hand, if you take any Kodaira dimension, except for kappa is 0, then you have also manifolds which are non-special and with kappa and of dimension n. Yes, another kind of example, if you have a holomorphic map, or even meromorphic, non-degenerate and meromorphic, then X has to be special. So if X, so you have X, and you have a priori transcendental holomorphic map from Cn, and here you have Xn, and even if you have a small subset, actually, which is reached by the image here, then this will be automatically special. So this is a kind of orbifold version of the theorem of Kobayashi-Yoshihari. Yes, now if we look at the case of surfaces, we have a very easy characterization, but unfortunately this is true only in this small dimension. If x2 is special, if and only if we have kappa of x is less than or equal to 1, this is certainly a necessary condition. And pi 1 of x, this is almost abelian. Almost abelian means that there is a finite index subgroup which is abelian, or equivalently you have a finite étal cover which has an abelian fundamental group. So we have this characterization for surfaces. So this is a very pleasant characterization. In particular, it shows that the class of special surfaces, this is closed under deformation and specialization. So this is something which is completely unknown in dimension 3 already, so we don't have. And maybe I use this because I still have, I will give a certain description maybe. And so we have another conjecture is the following, that x is special, which implies, should imply, this is, that pi 1 of x is almost abelian. So this is also something which is open for example, and in particular you see that you have here a topological obstruction possible to the potential density of rational points, for example. This gives you, I mention this because of next talk, for example, and I have seen this. So you have this gives you a topological obstruction to the potential density of rational points. So we have this. This is shown actually for representations of a fundamental group, linear representations of a fundamental group. So, so the statement being, if x is special and if you have a linear representation of a fundamental group, then the image is almost abelian. So this is true. So you have this, and now let me look at the, so the next step is now, of course, if C1 of x is 0, for example, and then does this imply that that there exists a dense H from C to x? And so in this situation, so this is very open, and we see that the proof that we have seen for in the case of rationally connected will certainly not apply, because this depends very much on the deformation theory of rational curves, which is very peculiar. And so we don't know how to prove this. In the case of surfaces, I would like to mention that we know that this is true for surfaces. For example, special surfaces satisfy this, with the exception, this is always the same one, of Caffrey surfaces, which are not elliptic, and not Kumar. But let me just make a small remark. In this situation, you have, I will stop here. You have infinitely many covering families of elliptic curves of such Caffrey surfaces. So it is, of course, very tempting to try to use them to make dense entire curves as we used rational curves. But here the situation is much more difficult. As we have seen, when we have two rational curves which are meeting like this, then we can approximate it by a rational curve. Here, but on the other hand, if we are given two elliptic curves, and here we have E1, E2, and so even both ample, for example, then in general we can't approximate them by there are arithmetic genus consideration which completely forbid to approximate them also by another elliptic curve, for example. But nevertheless, and this I don't know whether or not one could make transcendental entire curves close to this. I don't know. I didn't try to look at this. This is just to point out at how difficult the situation is now when we go from rationally connected to the class of C1 of x is 0, even in dimension 2. And so I will maybe stop here.